All right, everybody. How are we doing? All right, so we're on to the next topic here. We just kind of finished talking about solubility in class on Thursday, and we're going to change gears here to talking about sort of the last couple of things here, some more miscellaneous things at the end of this chapter here. And we're going to talk about something called electrolytes and ions in solution. The whole goal of this today is to introduce something called a dissociation reaction. All right, dissociation reaction. So let's talk about electrolytes and ions in solution. So first and foremost, an electrolyte is an ionic compound that conducts electricity in solution. And that might seem kind of wonky and like doesn't make sense, but truly there are substances like that. It's an ionic compound that conducts electricity in solution. So when you take this ionic compound and you pour it into a cup of distilled water, for example, and you stir it up, you're able to actually conduct electricity through that solution of that electrolyte. But here's the catch. Okay, we learned about soluble compounds the other day on Thursday, right? Soluble versus insoluble. Only ionic compounds that are considered to be soluble are going to be electrolytes, right? If they're not soluble, if they're an insoluble compound in water, they're not making a solution. They're making a heterogeneous mixture, right? So not the case. Okay, these are the only compounds that form aqueous solutions. Okay, in solution, ionic compounds dissociate into their ions. So whenever you pour in or put a spoonful of, let's say, that Gatorade powder I always refer to, right, or liquid IV, right? It's not like you're just pouring in that substance and it's dissolving into the water and that's it. What actually ends up happening is something like this. All right, so let's say, for example, you take a spoonful of table salt, NaCl, right, sodium chloride. You take a spoonful of that, you pour it into a cup of water, and stir and stir and stir and stir and stir. Eventually, after you continue to stir, you have now made a solution, where you took a solute and the solvent, combined those to create a solution. What actually ends up happening in the atomic level, way too small for us to actually physically see, what actually ends up happening is the NaCl compound breaks apart into its ions, Na plus and Cl minus. And this is exactly what happens here. You've got Na plus and Cl minus ions just kind of floating in your solution. Now, this brings us to these dissociation reactions. Well, a dissociation reaction occurs when you have some ionic compound that's soluble in water that dissolves into solution to create its ions, okay? So first and foremost, it's kind of similar. It's using almost the same skills we utilized in class on Thursday when we were utilizing our table F there, right? Are using this guy right here, and I'll go back and show you what I was talking about here, right? When we were doing all this stuff here, and we were identifying the different ions, right? You're identifying your positive ion and identifying your negative ion to use table F here. It's the same type of situation here for our dissociation reactions here, okay? Where did I go? I went too far. Here I am. Okay, so first and foremost, identify the cations and the anions that make up that compound. Second, the ionic compound itself, the full formula of the compound, goes on the left-hand side of the arrow as a product or as a reactant, and the ions, when they break apart, go onto the right-hand side as products. So the actual ion, the ionic compound itself is the reactant on the left. The ions that break apart are the products on the right-hand side. And these can only be written for ionic compounds that are soluble in water. So if it's not a soluble compound, if it's an insoluble ionic compound, you can't write a dissociation reaction for it. Okay, it has to create a solution. You also can't do this for covalent molecules, right? Covalent molecules are not going to create solutions. Okay, so you got to make sure you pay attention to that. So these first two examples, you've got MgCl plus 2, or sorry, MgCl2, right? And as we know, we have to be very good when it comes to utilizing our reverse crisscross method. So we've got MgCl2. And technically, there's an invisible 1 here. We've got the 2 as our subscript for chlorine and the invisible 1 here. This 1 will cross up to give us a minus charge for our chlorine, and this 2 will cross up to give us a positive 2 charge for our magnesium. So we've got now an Mg plus 2 ion, that's aqueous, plus the Cl minus ion that is also aqueous. All right. we have to make sure that we balance our equation. Okay, look at, we've got MgCl2. So we don't just have one atom of chlorine, we have to make sure we've got a coefficient, right? Thinking about balancing equations, we've got a total of 1 magnesium on the left here, and we've got 1 magnesium on the right, 2 chlorines on the left, and now 2 chlorines, goodness. 2 chlorines on the left, 2 chlorines on the right-hand side. Okay, so you have to make sure we balance that thing properly. Now, the next one up here, Ca3PO4, right? Same deal. Okay, it's going to break apart into its ions. So we've got Ca with a subscript of 3, PO4 is the ion. So around the parentheses there is a 2. So this 2 is going to cross up to be our +2 for calcium. And this 3 is going to cross up to be our -3 for our PO4. So this is going to break apart and turn into Ca +2 aqueous plus our PO4 -3 that is also aqueous. But again, making sure we balance. So we go back to the left-hand side. Our subscript of 3 here for our calcium tells us we have to have a total of 3 calcium ions on the right. And this subscript of 2 right here for our PO4 tells us we have to have a total of 2 PO4 ions on the right-hand side. Okay, so when we look at this all nicely and neat, 3Ca +2 plus 2 PO4 -3. Okay. So those are dissociation reactions. Now, moving away from that is something called colligative properties. And this is going to kind of be a component of the very last thing that we talk about for this chapter 13 here, colligative properties. All right. Colligative properties are the physical properties of solutions affected by the number of solute particles that are formed in solution. Okay, so here are a handful of different colligative properties that we're going to talk about. Vapor pressure lowering. And this occurs when adding a solute to a solution that lowers the vapor pressure of the resulting solution. You've also got something called freezing point depression. And this is what happens when you add a solute to a solution, which lowers the freezing point of the resulting solution. This is a really great example of why we place road salt on our roads in the winter. It helps, quote unquote, melt the snow. Well, in reality, you're actually not melting the snow. What actually happens here is this. You've got water that freezes at 0 degrees Celsius, right? So water freezes at 0 degrees Celsius. Well, freezing point depression means we are lowering something. So if we're lowering the freezing point to, like, let's say -15 degrees Celsius, that means our freezing point of the water, so, surrounded by all that rock salt we put there, right? It's lowering the freezing point from 0 degrees Celsius down to -15 degrees Celsius, which means the road salt is forcing the snow to essentially transition back to the state of matter of liquid, because the outside air temperature is not anywhere near that -15 degrees Celsius. So unless you want that snow or that liquid water to melt or freeze again, rather, it needs to be at least -15 degrees Celsius outside in order for it to start freezing again. So that's why we use road salt to clear snow and ice off of our, our walkways and our pathways and whatnot, because it helps. Actually, it doesn't melt snow or it doesn't melt ice. It lowers the freezing point of that water to make it transition back from the solid state of matter to the liquid state of matter, because you need a lower outside air temperature to freeze that water. It's not going to freeze at 0 degrees Celsius. It's going to freeze at lower, like maybe -15 or -20, depending on what kind of rock salt you're using. Okay, so that's freezing point depression. Now the opposite is kind of used in the effect when it comes to boiling point. Okay, boiling point elevation is when you add a solute to a solution that raises the boiling point of a solution, and this is why we sometimes add, salt to your water whenever it comes to boiling water. So, like, let's say, for example, you want to boil some pasta, right? Sometimes it's really important, for number one, for flavor, right? Because salt tastes really, really good. Okay, but number two, not just for flavor, but to actually speed the cooking process up, we add salt to our water when we were boiling pasta. And what that's going to happen is have the kind of exact same effect. So we've got boiling point elevation, which means we are going to be raising the boiling point of our substance. Well, as we know, water boils at 100 degrees Celsius. Okay, and actually, you know what? I'm going to move where this is right now. Okay. So water boils at 100 degrees Celsius. Okay. Now, if we add salt to our water, let's say our water might boil at maybe 115 degrees Celsius. Okay. So just by adding salt to our water that originally boils at 100 degrees Celsius, add salt, stir it up. Our water, our solution of salt water essentially, now boils at 115 degrees Celsius. Okay, so that water temperature, that solution of your salt and water now is at a higher temperature, 115 degrees Celsius. So 15 degrees higher than it would have originally without salt. That's going to allow your pasta to cook much, much faster because you've got a higher temperature cooking that pasta at a higher temperature essentially. So 15 degrees Celsius more, cooking that pasta. And the last colligative property we're going to talk about is called osmotic pressure. And this is occurring when adding a salt on the outside of something called a semi-permeable membrane, which increases the tendency for water to leave the inside of that membrane. We're not going to really focus too much on osmotic pressure, but a lot of our focus will be on boiling point elevation and this one back here, which is freezing point depression. So freezing point depression and boiling point elevation are going to be our main two we're going to talk about. So a couple more things on colligative properties. The amount of the boiling point elevation or freezing point depression depends on a handful of things. Okay, I'm going to talk more about these into next week on Monday. First and foremost, it depends on the number of ions that the substance dissociates into. So if you've got more ions coming from your dissociation reaction we just learned about a few minutes ago, the more ions, the greater the change of that boiling point or that freezing point. And again, this is only based on soluble ionic compounds that dissociate, creating a solution, right? No insoluble compounds and no covalent molecules, right? Only soluble ionic compounds. The concentration is also going to play into effect here, right? So the concentration in terms of your moles or your molarity, right? The greater the concentration of whatever you're adding to your water, right? For example, right? The greater the change. Right, so if you're going to add only one little piece of rock salt to your patch of ice, you're not going to really change much of your freezing point, right? You're not going to lower the freezing point, very, very much. Okay, same thing. If you're only going to add a small little pinch of salt to your very large, bowl of pasta water, right? You're not going to change or increase that boiling point much at all, right? But if you take a giant scoop full of salt and add it to your pasta water, that's going to really jack up the temperature at which it boils, right? So you're gonna have a boiling point elevation that's much, much more apparent, right? Because you've got a higher concentration of salt adding to your water there. And lastly, the amount of solute is also going to matter there as well, right? So the physical amount of solute you're adding, right? So the more solute you add to your solution, the greater the change in boiling point and the greater the change in freezing point. Okay. And that's all I've got for you guys today. I know this was a little bit of a longer video, but you had the whole weekend to kind of, gloss over it and listen to it and fill your notes out. But we'll chat more about all these different things in class on Monday. All right. See you then.